Okay, today we're going to learn about Newton's shell theorem. This is something that's just I want you as educated young men and women to be aware of. I don't think it's on the AP exam per se. And then we're going to learn about gravitational potential energy, which is on the AP exam. And then we probably won't have time to go through conceptuals because I didn't have time in my other two classes. So a Newton shell method, you don't even have to take notes. You can just watch and enjoy. I'm going to tell you Newton shell method. And here we go, and then gravitational field. Newton's shell theorem, I mean. Newton's, that's Isaac Newton. Newton's shell theorem. In doing his law of universal gravitation, he also did a lot of math associated with it. You know, he did invent calculus after all. He's a really smart guy. And so there ended up being two parts to Newton's shell theorem. The first part. The second. Hello. Yes, Sule.
What?
Yes, I do. Oh, like maybe 3 or 4. Yeah, sure. When are you going to need that? Oh, yeah. Do you want to just send a student and I'll give them?
Thank you.
I'm gonna beat you up with this blue.
What did I do?
Okay.
Who's that? Can I have a picture on the back of your chair?
Oh, very well.
Like right now?
What? You're the cutest. Do you want to get tutored?
Induction is like a whole software induction I would charge
When he like grounded. So like,
touch it, touch the ball.
so like you put the charge close to the thing, and then you touch the opposite side, and then you like move it. And then it should be down.
Okay. Oh, yeah, you're doing that. So Mrs. Haggerty's aide is going to come, and I'm going to give her all my playing cards.
Oh, Mr. Shana, Gavin wants to call you a liar, by the way.
Yeah.
Why?
Because Newton didn't invent calculus. Leibniz did.
Leibniz did. Are you aware of the huge?
I am. I did this with Mr. Morrison too.
Oh, really?
Yeah.
Leibniz. Yeah, you know, Leibniz was German, so we don't believe him. Newton was English, and they're our allies. Okay, guys, here comes Newton's shell theorem. Here's the first thing Newton's shell theorem says, and he figured this out mathematically. Imagine you've got a planet. Imagine you got some dude outside the planet, and it doesn't matter where he is. Okay, you might think, oh, how am I going to get the gravitational force that this planet exerts on the guy? Because part of the planet is near him and part of the planet is far from him. How do I deal with that? Well, Isaac Newton said, hey, guess what? You can just assume all of the mass of the planet is concentrated at its center, and that's good enough. That'll get you the gravity. It's the same thing. Calculating the gravity, trying to deal with the parts close and the parts far from him is identical to just saying, hey, all of this planet, you know, is concentrated at the center of the planet, and that's what you can make your calculations relative to. That's the first part of his shell method. Number 1, all mass of planet concentrated at its center. Concentrated at its center. For calculating gravitational force, and you don't even have to write this down if you don't want to. All mass of planet concentrated at center for gravitational force on object outside the planet. But what happens if you're inside the planet? What if you dig a big hole and you find yourself, you know, right there? Now, how are you going to deal with the gravitational force that the planet exerts on you? Well, now you have to think of something else. And this gets to his shell theorem. Isaac Newton said, okay, imagine you're inside a hollow sphere, although they called it a shell, like an egg shell. Okay, imagine you're inside a hollow sphere. So here's the hollow sphere. Tell me, so you get it. It's not a solid planet. This is a hollow sphere. What do you suppose the gravitational force on some guy at the very center of the sphere is going to be? What's that? What do you think? What's the gravitational force on a guy at the very center of the sphere, of this hollow sphere? Oh, please. Yes, Logan. Thank you very much, Logan. Why did you say 0? Okay, so you're thinking, hey, you know what? If I concentrated that shell at the center, then all of the shell would be concentrated where the dude is, and that'd be 0. Okay. Are you from Mrs. Haggerty?
Yeah. For the
All right. What's that? Yes.
The cards, yeah.
Yeah, here they are. And did you bring the lenses?
Yeah, I put them next door.
Oh, you did it next tomorrow.
Yeah.
Good
Thank
for
you.
Thank you. Okay. But someone give me another reason. Besides concentrating the mass at the center, there's another good reason why there's no net gravitational force on you when you're at the center of a hollow sphere. What would that other reason be? Okay, why isn't there a net force to the left? What if I claim to you, hey, if I'm at the very center of a hollow sphere, then the net gravitational force is to the left? Why would you laugh at me if I told you that? Why does it not make sense? Why does it go against common sense? If I tell you, I'm at the very center of a perfectly symmetrical, uniform hollow sphere, but I claim that there's a net gravitational force to the left. Why would that not make sense? Yes, Sean?
Because gravity's coming from one direction.
Thank you. And Jonathan, was that you? Is that your thought? Thank you, Jonathan. You guys okay with that? Because gravity's coming from all directions. Why isn't he feeling a force to the left? Because there's this thing to the right that's equal and opposite, right? Why isn't he feeling a net force? Whoa. Sorry about that. Why isn't he feeling a net force up? Because there's an identical sphere, part of the sphere below him. Are you okay? By symmetry, there's no net force. Okay, do you believe no net force when you're at the center of the sphere?
Yeah.
But now let me ask you this. Suppose I move there. Now, is there going to be a net force on me if I'm right there inside a hollow sphere? Okay, Earl, you say yes. In which direction?
To the right.
Why to the right?
You're closer to the right.
Beautiful. Is everybody okay with that? I'm closer to the right. That there's this portion, imagine it being like some sphere. There's this portion of the sphere that's really close to me. But there's only one problem. Yeah, this part of the sphere to my right is closer to me, but what do you notice about the part of the sphere to my left? What's that, Alejandro? It's bigger. There's more of it, right? There's more of it. There's more sphere to my left than to my right. Yeah, to my right is closer, so it exerts my force, but to the left there's more of it, so it exerts more force. So what do you suppose the outcome of that is going to be? What's the net force of this guy over here going to be? Well, let's do what Isaac Newton did. He says, okay, I'm going to make two intersecting lines right here so that I've got this portion of the sphere pulling me to the right, and I've got this portion of the hollow sphere pulling me to the left, okay? Let's suppose, just to make it easier on you little students, suppose this distance was r and this distance was 2r. This is half the distance, which means by what factor will it exert more force if it's half the distance? Inverse square law.
As much.
How many times? What's that?
Twice as much.
No, because it's inverse square law. Thank you, 4 times as much. So this is going to exert 4 times as much force because it's half the distance. But there's one thing. This is more than that. How much more? Well, this is an area. And you know, area is proportional to the square of the radius. So because this guy is twice as far away as that guy, how many times more area is this guy going to have? If it's twice as far away. What I'm asking is, if I have 2 identical objects, and one object has a radius r, and the other object has a radius 2r, how many times more area will this guy have than that guy? And remember, area is proportional to the square of the radius. Oh my God. They're seeing on video that you guys aren't answering.
Say it louder,
Is
please.
it 4?
Thank you, Gavin.
Radius
It's
nine.
4. You guys see that? So he's half as close, so each particle of this guy exerts 4 times the force. But here, this is 4 times the area, so each particle, I've got 4 times the particles. Each particle exerts 4 times the force, but I got 4 times the particles here. Do you see that those two forces are going to be equal and opposite? Okay? 4 times as much, but each particle exerts only 1/4 as much force. And in fact, that's true for any 2 lines I care to draw, right? I could do this. I could draw these 2 lines. And this area and that area, they will exert equal and opposite forces. Because even though there's less area here, it's closer. Even though there's more area here, it's farther away. And they exactly cancel each other. So the second part of Newton's shell theorem says that everywhere inside a hollow shell or a hollow sphere, the gravitational field is 0. Gravitational field equals 0 everywhere inside a hollow sphere. Boy, it's like pulling teeth with you guys. Maybe I should just talk and not ask you guys questions. Okay? So here comes the corollary. There's a corollary to his rule that the gravitational field is 0 everywhere inside a hollow sphere. What if I've got a planet and but this is a solid sphere. This isn't a hollow sphere anymore. It's a solid sphere. What's the gravitational force when I go inside the radius of the planet? What's the gravitational force right there going to be? Well, here's the way Isaac Newton thought about it. He said, I'm going to consider this surface to be an annular ring of the planet. Imagine it's Earth, but it's only the outer 10 meters of the Earth, let's say. So I've got this annular ring of Earth, just the outer 10 meters of the Earth. Tell me, how much gravitational force is this shell of Earth exert on this guy right here? How much gravitational force? Only this annular ring of planet Earth, only that black ring. How much force does that black ring exert on that guy right there? I'm going to have to call on, who said that? Thank you, Alejandro. Say it again. 0, right? 0. So I go, okay, so that part of the planet isn't exerting any force on this guy. Let's go to the next 10 meters. Let's go ahead and look at this annular ring of Earth. This shell. Tell me, how much gravitational force does this purple shell exert on that guy? Am I going to have to call on Alejandro again? Noel, how much force is the purple shell exerting? Thank you. 0? Okay. So let's make another shell. Let's go even farther down. How about this orange annular ring? How much force is that orange ring exerting on that guy? Yes? Thank you.
I'll answer your question.
No, oh gosh, he knows. Okay, in fact, are you guys getting that all of the annular rings until you get to where this guy is exerting no gravitational force on him? By this guy entering into the Earth, he has effectively reduced the size of the Earth. All of the Earth beyond this radius is exerting no net force on him, because all of the Earth beyond him can be thought of as hollow spheres that all cancels each other out. Okay? So when you go inside the Earth, you are reducing the size of the Earth. Okay? So now we've got to consider 2 things. Let's say the distance he's gone is AR, where A is less than 1. Okay? he's gone some fraction of the radius of the Earth. He has reduced the size of the Earth. I want you to see that because of inverse square law, he is closer to the center, so the force has gone up proportional to, well, inversely proportional to the square of the radius. The force is increasing because he got sent closer to the center of the Earth. But the problem is the mass of the Earth got reduced, right? You reduce the size of the planet. You reduce the mass of the Earth. Because all of this Earth out here isn't contributing to the gravitational force on you. So you've reduced the mass of the Earth. And the mass has gone down proportional to the cube of the radius. You see? Because volume is 4/3 pi r cubed. So if you cut the radius in half, you've cut the volume to 1/8 of what it was, and thus you've cut the mass to 1/8. So because the mass has gone down proportional to the cube of the radius, but the force is going up proportional to 1/r², that means that the net force is going to go down proportional to the radius. That is, if you cut the radius to 2/3, if this guy right here is 2/3 r, then your gravity, your gravitational field, is going to be 2/3 what the gravitational field is at the surface of the Earth. Okay? Or if I chose another point, if I chose a point that was like half, if I said this was a radius of half times the radius of the Earth, half, then the gravitational field is going to be 1/2 times the gravitational field of the surface of the Earth, right? Because I'm gaining force proportional to 1/r², but losing mass proportional to r³, which means I'm going to lose force proportional to r. Or finally, let's say I have this point here. Let's say that this is 1/4 the radius of the Earth. Then g would equal 1/4 times the gravitational field at the surface of the Earth. And that's the corollary, Newton's corollary to what happens when you're inside a solid planet. If you're inside the planet at radius equals a times the radius of the planet, okay, where 0 is less than a, which is less than 1, then the gravitational field is going to be a times the gravitational field at the surface of the planet. Hey guys, that's it. That's all I wanted to tell you about Newton's shell theorem. Interesting. If anyone asks you, that's what you'll tell them. If they ask you, what's the gravitational field halfway to the center of the Earth, just tell them it's a half g. Any questions or comments or thoughts? All right, well then, hey, let's do gravitational potential energy. And you've extinguished my asking you questions behavior, so I'll probably just talk about it. There you go. Oh, I got a problem here. Just a second. What's going on with this thing? Just getting streaks. Okay. Gravitational potential field. Gravitational potential energy not at a planet's surface now write this down. This is something you have to know. Here's the way we used to do it. I would say, well, if I have a mass that's some height h above the Earth's surface, then I'd say that mass has a gravitational potential energy, which, by the way, I'm going to start using the AP exam nomenclature for gravitational potential energy, which is a capital U sub G. They use capital U for energy. So U sub G, so the gravitational potential energy is going to equal mgh. I get to say this for two reasons. Number one, because I define the surface of the Earth as h equals 0, which means that the surface of the Earth, the gravitational potential energy is 0. And I assume that at the surface of the Earth, the gravitational field is uniform. That is, the gravitational field is never changing. Okay? That is, whether I'm 10 meters or 20 meters or 30 meters above the Earth, the gravitational field is about the same, so I can just use mgh. But there's two problems with that. Number one, defining the surface of the planet as 0 gravitational potential energy becomes tricky when you start having several planets involved. If I have some guy here and I say, what's his gravitational potential energy? Well, whose surface are you going to measure it relative to? You see, that gets a little tricky. So we don't want 0 gravitational potential energy to be at the surface of a planet anymore, not when we're dealing with multiple planets. And then secondly, as you get farther and farther from your planets, your acceleration of gravity is changing. The gravitational field is getting less and less. You don't get to assume uniform gravitational field like you do near the surface of the planet. So I've got to think of another way now to get gravitational potential energy, and here it is. Here it comes. The first thing you should know, we are no longer going to say 0 gravitational potential energy is at the surface of a planet. We're going to say 0 gravitational potential energy is infinitely far away from the planet. 0 gravitational potential energy at infinity. Let me show you what that looks like. You have to get a new towel. Suppose I have a planet here. And suppose I have a mass there. Okay? Right now, this mass has 0 gravitational potential energy because it's at infinity. It's infinitely far away from that planet. This is my planet. Okay? It's at rest, so its kinetic energy is equal to 0 as well. But imagine that I let the planet go. So the planet starts moving. I'm sorry, I let the mass go. So the mass starts moving. And because here it's feeling an infinitesimal attractive force to the planet, a teeny tiny attractive force, but as it gets closer and closer, it's feeling more force. Okay? As it gets closer, what's happening to the kinetic energy? Oh wait, I promised myself I wouldn't ask you any questions. So as it gets closer, the kinetic energy is getting bigger. It's getting more positive. But this is a conservation of energy situation. There's no work being done by non-conservative forces. So if they both start with 0, and I can't help myself, I'm going to ask you guys, because they both start with 0, and now the kinetic energy became positive, you tell me what just happened to the gravitational potential energy. Remember, they have to add up to 0. Thank you very much for saying that, DeAndre. You made my day. Yeah. Okay, and as it gets closer, the kinetic energy is going to become more positive, which means my gravitational potential energy becomes more negative. Then it's really close, and I have a huge negative gravitational potential energy. Why? Because I got a huge positive kinetic energy. You see? And that's the way it works. When we're not at a planet's surface, we're going to end up having our gravitational potential energy always being negative, because I'm assuming 0 gravitational potential energy infinitely far away. And when you're infinitely far away, as you get closer and closer and gain the kinetic, you're going to have to lose gravitational. It's going to become more negative. Or here, maybe let me put it a different way. Okay, here's my planet. Let's say I have a mass here. Okay, and I want to send it to infinity. How much kinetic energy am I going to need to send that planet to infinity? That much. So I'm going to need that much kinetic energy to send it to infinity, right? So I've sent this mass to infinity, and let's say I just gave it just enough kinetic energy so that it barely escapes the gravitational field of this planet, so it barely makes it to infinity. So it gets to infinity, and it's got 0 kinetic energy. By the way, at infinity, how much gravitational potential energy does this guy have? 0. Good for you guys. Which means back here, whatever kinetic energy I needed to send that guy to infinity, how much gravitational potential energy did it have at that time? It's got to end up with 0. Both of them end up 0. So whatever this guy was, what's that guy going to have to be? Yeah, the negative of it. You see? So that's the way you're going to have to think about gravitational potential energy now. It is now time for me to give you the formula for gravitational potential energy, and here it is. The gravitational potential energy for two objects, you know, whatever, close to each other but not at a planet surface or whatever. Here it is, negative G m1 m2 over r. If you're wondering why it looks like this, I'm going to tell you now, but you need to be in calculus to understand it. So if you're not in calculus, just zone. My gravitational potential energy is the amount of work gravity does to take this thing to 0 potential energy land. So over here, gravity was doing work, right? Gravity was exerting a force, mg, over a distance, h. And so the work gravity did in sending this mass from here to 0 gravitational potential energy land was mgh. But that's not happening now. Now that we've defined 0 gravitational potential energy land as infinity, what kind of work is the gravity of this planet doing as this mass goes to infinity? Positive or negative? Yeah, negative, because the mass is going that way, but this planet is pulling that way. You see, it's not like here, where gravity is pulling that way and the mass is falling that way, so I get to have a positive gravitational potential energy, because positive work is being done. Here, the planet's doing negative work. And you know how work is equal to force times distance? I've got a problem, because the gravitational force is changing as I go. So I can't just multiply mg times h, because my force is changing. It's not a constant force. So I'm going to have to say, okay, my force is g m1 m2 over r squared, and I'm going to calculate that force for some small radius, which I'll call delta r. And then when I've gone delta r, I'll recalculate that force and multiply by a new delta r, so that my work that this planet does, which by the way is negative because the force is that way and the mass is going that way, this work, well, no, I won't even do that. I'll just say the work is going to be the sum of the g m1 m2 over r squareds times all of the delta r's. Well, those of you in calculus may recognize this. What am I going to replace that sigma with? Yeah, integral symbol. This ends up being the integral of g m1 m2 over r squared dr. And you tell me, what's the antiderivative of g m1 m2 over r squared? What's the antiderivative of that? that. Are you guys okay with that? So that's where this comes from. So now you're going to use this. This is why gravitational potential energy is negative. And problem number 5, I don't know we're going to have, because I was going to ask you to get the gravitational potential energy of the Earth mass system, but I'm not going to do it. But all you'd have to do is plug in mass of Earth, mass of Moon divided by the radius. So it's a nothing problem. So do problem 5 on tonight's homework using that formula. But I got to tell you one more thing about gravitational potential energy. The second thing you should know, it takes 2 masses to have gravitational potential energy. You must have 2, or more masses to have gravitational potential energy. One way the AP exam will try to fake you out is they'll say, what's the gravitational potential energy of the Earth? And the answer is there is none. You can't have gravitational potential energy of one thing. You need 2 things to have gravitational potential energy. If there's only one mass, you can't talk about gravitational potential energy. You need 2 and then use that formula. And good luck on number 5. I'm depending on you guys doing that problem because I didn't get you to have you do the math, the Earth-Moon thing. So what am I telling you? On problem 5, just mindlessly use that formula. And now we say bye-bye.